Hello, everyone. Welcome to the second lecture of our course on heterogeneous systems. After the introduction that we had last week, today we are going to give a brief lecture to introduce the architecture and programming model of SIMD processors and GPUs. This is a brief lecture that will later point you to a longer version of this lecture that is also recommended for sure. So let me very briefly remind you that in current computing systems, it's more and more frequent to find a plethora of heterogeneous devices that are specialized for different functions. In this pictorial representation here, we have CPU cores, GPU cores, and FPGAs or reconfigurable fabric. These can have a unified view of the memory and can exchange data through coherent interconnects. In this course, we are focusing on these type of systems with an emphasis on GPU programming. That's why we have started the course with classifying the computers on three main classes or three main types according to Flynn's taxonomy. Remember that the other day we highlighted SIMD processors that are processors where a single instruction stream operates on multiple data elements. And we mentioned that array processors and vector processors are the classic examples of SIMD processors. We start with SIMD processors because they are the basic paradigm of GPUs, which are let's say the accelerator of choice for many important applications these days. Let's talk about SIMD processors and about the architecture of GPUs. First of all, SIMD processing, remember, is a single instruction operating on multiple data elements, and this can happen in time or in space. We are going to assume that we have multiple processing elements or execution units, and this time-space duality basically defines the two types of SIMD processors that we can have. The first one is the array processor, where one instruction operates on multiple data elements at the same time using different spaces. And the second one is the vector processor, where a single instruction operates on multiple data elements in consecutive time steps using the same space. Here you have your first example of array processor and vector processor. And on the left-hand side of the slide, you can see our first vector or SIMD processing program. As you can see, this is an instruction stream where we first load few elements of an array A into a vector register VR. Then we perform an addition on the elements, on the 4 elements that we loaded into this VR, then perform a multiplication, and finally we store the result in the same array that was the source of the values that we have operated on. So let's first see how we execute this instruction stream on an array processor. Because the 4 processing elements are the same and they are capable of executing different instructions, we can have the 4 processing elements of the array processor performing one of the 4 load operations that come with the vector load in the instruction stream. So that's why P0 takes care of loading element 0, P1 takes care of loading element 1, and so on. After that, they perform an addition. When the addition is complete, they perform a multiplication, and finally, they can store the result back in memory. In the case of a vector processor, as you can observe, we have different processing elements, but these processing elements are specialized. There is one processing element for load, another one for add, another one for multiplication, and another one for stores. So if we want to load 4 elements, we'll have to use this LD unit. And that's why in the first cycle, we start loading LD0, then LD1, then LD2, and then LD3. And observe that as soon as we are done with one specific element, LD0, we can start computing the rest of operations, add 0, mul 0, and store 0, and so on and so forth. So as we can see, there is a key difference between the array processor and the vector processor. In the array processor, we are performing the same operation at the same time while in the vector processor, we perform different operations at the same time. And in terms of space, in the array processor, we perform different operations in the same space, while in the vector processor, we perform the same operation in the same space. As we see, they are two different paradigms, but both are SIMD processors, and they are very similar in the fundamental ideas that are behind them. Let's start talking about vector processors. A vector is a one-dimensional array of numbers, and many scientific and commercial problems use vectors. In the example, this example code that you can see on the slide, we are operating on two vectors, A and B, and we are storing the result in one vector C. Observe that the three vectors, A, B, and C, have in total 50 elements, or at least we are operating on 50 elements of these vectors. A vector processor is one whose instructions operate on vectors rather than scalar values or single data values. But to do so, there are some basic requirements. First of all, we need to load and store vectors. So we need to read from memory and put the values that we read into some registers that are called vector registers because they contain vectors, right? Not a single value, but a vector of values. The second requirement is that we need to operate on vectors of different lengths. In principle, there's going to be a maximum length, but we can configure the length that we want to use, and that's the vector length register. In the example code that we have in this slide, the vector length would be 50. And the third requirement is that the elements of a vector might be stored apart of each other in memory. So that's why we need to use a vector stride register. That defines what's the stride of the accesses, load or store accesses, when we go to memory and fetch data that we will put into the vector register. The stride is the distance in memory between two elements of a vector. The vector registers hold, the size of a vector register is n, and that means that the vector register can hold n bit values, or in other words, the size of the vector register in bits is n times m. There are also control registers or vector control registers. We have already mentioned two of them. The first one is the vector length. The second one is the vector stride. And there is a third one that is the vector mask that we are going to use for conditional operations. We will speak about them later. The maximum vector length, as I said, can be, there is a maximum value, let's say n, but we can configure it depending on the specific needs of our program. And the vector mask register is going to indicate whether we operate on a specific element or not. We will see an example later. Remember that one of the requirements is that we should be able to load and store multiple elements, right? And these elements can also be separated by a constant distance that is called the stride. For now, we are going to assume just a stride 1. The elements can be loaded in consecutive cycles if we can start the load of one element per cycle, but we should be able to sustain this throughput of one element per cycle. How can we do that if one single memory access will likely take more than one cycle? The solution to that is to use a banked memory or an interleaved memory, where we partition the memory into multiple banks or multiple pieces of memory that we can access independently. And what we are going to do is to interleave the elements across the banks. This is an example of a banked memory with 16 memory banks. Observe that for each of the banks, we have a memory data register and a memory address register. What this means is that using the address bus, we can place a different address in each of these MAR, and we can request some specific values, some data from the bank. That data or that value will be copied into the MDR for it to be moved through this data bus. So memory is divided into banks that can be accessed independently, and these banks share the address and the databases, as you can see. What we can do here, because these buses are shared, is that the CPU can issue one access per cycle. Because the access to memory itself takes more than one cycle, what that means is that after certain number of cycles, we will start obtaining one value in this MDR every cycle. So if we have n banks, we can sustain n concurrent accesses, 16 in our example. What is necessary for a program to be written for a vector processor or a SIMD processor? It's important that the code is vectorizable. For example, what happens if we have a loop? A loop is vectorizable if each iteration of the vector is independent of any other. For example, here, we can compute the addition of AI and DI in a completely independent manner of other values of I. That's why this loop is vectorizable, and that's why we can, instead of writing this sequential program, we can write a vectorized program or a SIMD program. Observe that the very first two instructions are just defining the vector length, 50 in our example, because we have 50 iterations in this loop, and the vector stride is just one, because we are accessing consecutive elements of arrays A, B, and C, or vectors A, B, and C. The next thing that we do is loading elements, or loading the elements of A into vector register 0, loading the elements of B into vector register 0, then we add them. Next, we shift right 1, which is the same as dividing by 2, as you know, and then we store the result in the corresponding addresses of vector C. One thing that I would like you to notice here is that some of these instructions take different amount of cycles. For example, the first two take just one cycle, while the load and store operations take 11 cycles, and the addition takes 4 cycles. However, because this is a vector processor, we can it's pipeline as well, same as the memory access to the banked memory. What that means is that after having paid the latency of the first access to memory or the first addition, in this case, we will get one result every cycle. So that's why the entire vector load operation is going to take 11 cycles, that is the latency of a single memory access, plus VLEN minus 1, 49, which are the remaining elements that we will start obtaining one cycle after the other when executing this vector load instruction. In total, here we have 7 dynamic instructions, and we will see how we execute them. For now, we are going to assume there is no chaining in our vector processor. That means that we cannot forward one element that was just obtained from a functional unit to the next functional unit. So we have to wait until the entire vector register is complete and is ready. And we are going to assume just one memory port for now. So we can just sustain one memory access at a time. And we are also going to assume that the memory is a banked memory of 16 banks, and it's word interleaved. We choose a memory of 16 banks because this way it's a power of 2, and it's a power of 2 that is larger than is larger than 11. That is the total latency. So what that means is that while we are waiting for the first element to come, we are waiting for these 11 cycles, we can continue issuing accesses to other memory banks, and this way we can hide the overall latency of these of the accesses to all the different banks. So if we execute our program in a vector processor of these characteristics, we will first spend 2 cycles on loading vector length and vector stride. Then we have these 11 plus 49 cycles that correspond to the first vector load. Then 11 plus 49 more cycles for the next vector load. Then 4 plus 49 for the vector add. Then we have the shift operation, and finally we have the store operation. So in total, this takes 285 cycles. Now, Let's see how we can optimize this. And one way of optimizing this is performing chaining, which is data forwarding from one vector functional unit to another. Basically, if we have obtained both the first element of A and the first element of B at this point in time, we can already start executing the first addition that adds A0 plus B0, right? So that's why we can forward the element A0 and the element B0 to the functional unit that executes the additions and start executing the addition. And as soon as we are done with the addition of A0 and B0, we can forward it to the unit that executes the shift operation, and we can start this shifting of one position to the right or one bit to the right in order to perform the division. If we do so, we can reduce the total number of cycles here, and it will be from 285 in the previous slide to 182 cycles. But we can further optimize this code. Why? Because these two loads could be done at the same time, while this load and this store can also be done at the same time. But to do so, we need to increase the number of ports that we have in each memory bank. For now, we just assume a single port per memory bank. Now we are going to assume 2 load ports and 1 store port in each bank. That means that we can sustain 2 loads at the same time, and they can also overlap with 1 store. And that's basically what is happening here. Observe that the vector load of vector B overlaps with the vector load of vector A, and at some point they also overlap with the store, because as soon as we start computing, as soon as we read A0 and B0, we can perform the addition for these two elements, then the shift, and then we can start the corresponding write into C0. So we can further optimize this code, as you see, and or the execution of this code on our vector processor, and as you see, in total, it will take 79 cycles. So in total, 19 times performance improvement with respect to the execution, the sequential execution. Remember as well that we have a vector mask in our SIMD processor, and this vector mask is used to implement mask operations. We will need to use mask operations whenever we have conditions, and which means that in some cases, some values will satisfy the condition, in other cases, they won't. And based on that, we will execute the operation on the vector register or not. And here you can see the vectorized code for this sequential loop that you have here. We need to check if AI is 0 or not, because if it's not 0, then we'll perform this multiplication. But if it's 0, because it doesn't make any sense to multiply by 0, right? The result we already know that is 0, so we will skip it, right? And to do so, what we have to do is generating this vector mask. We generate the vector mask basically by checking the predicate of the condition, and based on that, we will obtain a mask bit per lane, per element of in the vector arrays, and we will execute the subsequent operations or not. So depending on what's the value of this vector mask, we will execute this mul and this store for some vector for some elements in the vector register or not. This is what is called the predicated execution, because the execution is predicated on the mask bit. There are also some more issues to take into account when using SIMD processors. Important issues are the relation between the stride and the banking. Remember that we have started assuming that we have a bank memory and that the stride is 1. If the stride is 1, there is no problem, because we can access all banks at the same time, because the words are interleaved on the banks. But what could happen if we have 16 banks and the stride is 2? That means that we have accesses to bank 0 and bank 2 and bank 4 and so on. And if in total we have 16 accesses, that means that we will have 2 requests to bank 0 for element 0 and element 8, 2 requests to bank 2 for element 2 and element 10, and so on and so forth. And one problem with that is that banks may not be able to sustain more than one access at a time, especially if they don't have more than one port. That's what we call bank conflicts. And the only way that we can avoid bank conflicts, I mean, there are ways of avoiding bank conflicts, but let's say that the only way that we know that there is not going to be a bank conflict is when both stride and number of banks are relatively prime. For example, 1 and 16 are relatively prime, or 3 and 16 are relatively prime, but 2 and 16 are not relatively prime. And this happens sometimes when we access matrices. For example, if we are going to perform a matrix multiplication and we need to access AV by rows, we need to access matrix A by rows, but matrix B by columns, there is a stride between the consecutive accesses to the same column, and that means that there is a stride, and if this stride is not relatively prime to the number of banks, we will have bank conflicts. How to minimize bank conflicts? The first solution is to have more banks. The second solution is to have more ports in each bank. We can also change the data layout in order to match the access pattern. I just gave you the example of the matrix B. So one thing we could do is transpose in matrix B in order that we access the columns horizontally as if they were rows. But this might not be possible in all cases. And then we can also figure out ways of doing better mapping of addresses to a bank. For example, randomized mapping. And this is a very good paper, seminal paper on pseudo-randomly interleaved memory that explains how to do, or at least one approach to do this randomized mapping. Okay. Remember that SIMD processors are almost everywhere these days, or are in many places these days. I mentioned in the previous lecture SIMD operations in modern ISAs. We were talking about this example of MMX instructions, how to do the overlay of a human on top of a background image, and we were reviewing how to perform these operation using MMX registers and using these MMX instructions. The MMX instructions were the first SIMD extensions of x86 processors. They were for, so the total width of the MMX registers was 64 bits and for integers. And after that, there have been successive improvements of these SIMD extensions. First one was the streaming SIMD extensions with registers of 128 bits for integers and single precision floating point. SSE2 includes support for double precision computation. SSE3 includes new instructions. SSE4, again, new instructions and also shuffle operations to move data between different SIMD lanes or different parts of the vector register. And later, the advanced vector extensions appeared with 256 bit floating point computation first, then 256 bit with floating point computation with fuse multiply add that executes one multiplication and one addition in a single cycle, then the extension to 512 bit, and more recently the advanced matrix extensions that are designed for AI and ML workloads. But SIMD operations are not only in modern CPUs, but also in modern machine learning accelerators. And I gave you last week the example of the Cerebras wafer scale engine that is the largest ML accelerator chip. But if we want to talk about a prime example of SIMD processors these days, these are graphics processing units or GPUs. Remember this big picture of this floor plan of the A100 GPU, where we can see a lot of homogeneity because there are many replicated GPU cores. But if we look at the internals of the GPU cores, we will see that they are very similar to the array processor and the vector processor that we explained in the beginning of this lecture. I remember that the A100 core, for an example, has multiple different execution units, such as these ones for load and stores, or these ones for integers, or for floating point operations, or the tensor cores that are also SIMD units that are specialized for deep learning. But at the same time, these are replicated, and these are replicated means that we can we can operate on multiple instances of the vector registers at the same time. Another important commonality between this A100 core and the traditional view of SIMD processors is that this one also uses banked memories, and this shared memory here is a banked or interleaved memory. And in order to be able to sustain multiple accesses to multiple elements that are going to be used by the corresponding SIMD units that we have in GPUs. Because GPUs in the end are just SIMD engines underneath. There is an instruction pipeline that operates like a SIMD pipeline. However, the key difference is that programming is not done with SIMD instructions, but using scalar threads. We will see how, and we are going to talk a lot about that in this course. So, but to understand this, we are going to go back to our parallelizable example, parallelizable code example, but first, we are going to distinguish between programming model and execution model. Programming model refers to the software, the way we write a program. For example, I just said GPUs are not programmed using SIMD instructions, but they are programmed using scalar threads. What is different is the execution model that refers to the hardware, how instructions are executed onto the existing hardware. As we will see, we can write code for threads, but the hardware can later take these threads, put them all together into a SIMD unit as if they were SIMD instructions and execute them onto the underlying SIMD hardware. So programming, just to recap, refers to how programmers expresses the code. Execution model refers to how the hardware executes the code underneath. And they can be very different. And one example are GPUs. Let me go back to the previous parallelizable code or vectorizable code that we saw earlier. If we execute this on a sequential machine, we will first execute iteration 1, then iteration 2, and so on and so forth. But one thing that we can realize here is that each iteration is independent. And because they are independent, they can all be executed at the same time. And a programmer or a compiler could generate a SIMD instruction to execute the same instruction on multiple data elements at the same time. So this is one vector instruction, this is another vector instruction, another vector load, this is a vector add, and this is a vector store. And these can be executed on a SIMD processor, either a vector processor or an array processor. But we can also write the program in a different way. We can also realize that this is each iteration is independent, and now we can generate threads. Instead of SIMD instructions, we can generate threads such that each thread executes one iteration of this vectorizable loop. This is what we could do, for example, in a mini machine, such as a multi-core CPU, for example. We can assign successive iterations to successive cores in our CPU. But we can also do that on a GPU. This particular model is called single program multiple data because we are writing one single program for one single thread, but this thread is not just one thread, it's multiple threads, and depending on the thread ID, they are going to operate on different data elements. This program can also be executed on a SIMD machine, and that's basically what GPUs do. That's why this is also called single instruction multiple thread machine. But a GPU is just a SIMT or a SIMD machine. The only exception is that it's not programmed using SIMD instructions, but it's programmed using threads, using an SPND programming model, where each thread executes the same code, but operates on different pieces of data. And each thread has its own content, it has the PC, they can be treated, restarted, and executed independently, but then the hardware are going to put all these or many of these different threads together, forming what is called a warp or a wavefront. For AMD, warp is an NVIDIA terminology, while wavefront is AMD terminology. But the one warp is basically a SIMD operation formed by the hardware. So what the hardware is going to do when receives all these instructions for individual threads is that it's going to put them together in a SIMD instruction that is called a warp instruction. So this would be instruction X for warp 0. This could be instruction X plus 1 for warp 0. This is x plus 2 for warp 0, and so on and so forth. So graphics processing units are SIMD not exposed to programmers. While SIMD is just a sequential instruction stream of SIMD instructions, SIMT, a GPU, is multiple instruction streams of scalar instructions that are later grouped. The threads are later grouped dynamically into warps. This has two advantages. First, that each thread can be treated independently. Threads can completely go through different data paths, control flow paths, while the threads can be grouped flexibly or potentially grouped flexibly. So just to summarize about how GPUs work, they have warps. These warps are collections of threads, all of them executing the same instruction as if they were a SIMD instruction. But another important characteristic is that the execution of warps is interleaved on the same pipeline. This is what is called fine-grained multithreading, and in GPUs we do fine-grained multithreading of warps. So for example, we can first start executing an instruction for warp 0, then we execute an instruction for warp 1, then another instruction for warp 20, etc., etc. So in summary, a warp is a set of threads that execute the same instruction, and these instructions for these different warps are executed in an interleaved manner using the same pipeline. This technique is called fine-grained multithreading. It's used in CPUs as well, as you might know, and has the key advantage that it enables to tolerate long latency operations. For example, accesses to the external of-chip memory. You are executing instructions for a warp, and at some point, this warp needs to go to memory to fetch data. And this is an operation that may take hundreds of cycles. While this warp is going to memory to fetch the data, other instructions from other warps can be executed on the pipeline, and this way take advantage of the existing resources. So to summarize, a comparison between warp-based SIMD and traditional SIMD is that in traditional SIMD, we have a single thread, and this single thread executes SIMD instructions. The programming model is SIMD. There is just one thread, but vector instructions or SIMD instructions. While in warp-based SIMD, we have multiple scalar threads. They don't have to be, the programmer doesn't need to assume that they are going to execute all together. Each thread can be treated individually, but even though the ISA is a scalar, the GPU will later form the SIMD instructions using these individual threads. So this is, in summary, the SPMD programming model executed on a SIMD machine. So it's SPMD is a programming model where each processing element executes the same procedure. These procedures are called threads, and they can these procedures or these threads can synchronize at certain points in programs with using barriers, and we are going to talk about barriers starting from the next lecture. And these multiple threads or instruction streams execute the same program. So that's the modern way of programming GPUs, of programming SIMD hardware, that makes it way more efficient in terms of programming, while if the programmer is skilled enough, still take advantage of all the execution parallelism that SIMD architectures can provide. And that's why in this course, we are going to put a lot of emphasis on optimizing code to make the execution efficient on these underlying SIMD hardware. This was just a brief overview of the architecture and programming model of SIMD processors and GPU, but I can recommend you this lecture from a previous semester where we cover all these ideas and all these concepts in much more detail. You can also learn more if you take a look at the book Programming Massively Parallel Processors in its 4th edition, in particular, chapter 1 and chapter 4 that talk about the architecture of GPUs. This is all for today. Thank you very much for your attention. Please keep an eye on the longer lecture as well, and I hope to see you in the in lecture 3 of our PNS on heterogeneous systems. Thank you very much for your attention.